Prime numbers constitute the non-decomposable building blocks of integers under multiplication. Their sequence appears irregular and chaotic when viewed along the linear axis of natural numbers. Analysis of their global density requires a shift from discrete arithmetic to the continuous domain of complex functions. Euler established a fundamental identity linking a sum over all integers to a product over all primes. The zeta function of s equals the sum of 1 over n to the power of s. This identity remains valid for all complex numbers with a real part greater than 1. The variable s consists of a real part sigma and an imaginary part t. Visualizing the zeta function requires mapping this two-dimensional input to a two-dimensional output. We observe how the function behaves as a conformal map, preserving angles except at specific singular points.
The initial series diverges when the real part of s is less than or equal to 1. Through analytic continuation, we extend the domain of the zeta function to the entire complex plane. The function remains holomorphic everywhere except for a simple pole at s equals 1. Riemann discovered a functional equation that relates the value of zeta at s to its value at 1 minus s. This symmetry involves the gamma function and powers of pi. It demonstrates a reflection principle across the vertical line where the real part equals 1/2. The functional equation forces the zeta function to vanish at specific points on the negative real axes. These are the trivial zeros located at -2, -4, -6, and so on. They offer little information about the distribution of prime numbers.
The non-trivial zeros are confined within the critical strip, where the real part of s is between 0 and 1. Riemann conjectured that all these zeros lie precisely on the critical line, where the real part is exactly 1/2. This remains the most famous unsolved problem in mathematics. The first non-trivial zero occurs at approximately 1/2 plus 14.13i. The second follows at 1/2 plus 21.02i. As we move higher up the critical line, the density of zeros increases logarithmically. The function pi of x counts the number of primes less than or equal to x. Gauss conjectured that this is approximately the logarithmic integral of x. The Riemann hypothesis provides the tightest possible bound on the deviation between these two values. Riemann derived an explicit formula expressing the prime counting function as a sum over the zeros of the zeta function. Each zero acts as a frequency in a giant Fourier series. These frequencies determine the fluctuations of primes around their average density. If the Riemann hypothesis is true, the error in the prime number theorem grows no faster than the square root of x times the logarithm of x. This represents a random walk behavior, suggesting primes are distributed with maximum possible entropy. The vertical gaps between zeros are not random, but exhibit repulsion. Montgomery discovered that the pair correlation of these zeros matches the eigenvalues of random matrices from the Gaussian Unitary Ensemble. This suggests a deep link between number theory and quantum mechanics.
The Hilbert-Polya conjecture posits that the zeros correspond to the energy levels of a quantum system whose classical limit is chaotic. In this framework, the Riemann hypothesis is equivalent to the requirement that the underlying operator is Hermitian, ensuring real eigenvalues. Supercomputers have verified that the first 10 trillion zeros all lie exactly on the critical line. While numerical evidence cannot provide a proof, the statistical alignment with the hypothesis is overwhelming. No counterexample has ever been found in any range tested. Many modern cryptographic algorithms and primality tests rely on the assumption that the generalized Riemann hypothesis holds. A proof would confirm the efficiency of these algorithms and the hardness of certain integer factorization problems.
Resolving the Riemann hypothesis would unite arithmetic and analysis into a single coherent framework. It would reveal the ultimate architecture of the primes and the hidden spectral laws governing the integers. The quest for a proof continues to drive the evolution of complex variables.